In this video, we're going to talk about flow graphs. Flow graphs are built around decision points, like if statements and while loops. They're graphical representations of a program's cyclomatic complexity. Here's an implementation of the square root function that we introduced in the last video. Let's look at the flow of this program. First, we declare some variables. That's strictly sequential. Then we set the min and max depending on whether the value of n is less than or greater than 1. Recall that 1 was a boundary point for n. Then we have a while loop that runs until the estimate or guess is within the requested accuracy. Inside the while loop, we have an if statement. If the guess is within the requested accuracy, we will effectively break out of the loop. If the guess is not within the requested accuracy, we check if the square of the guess overshoots the original value. If so, we set the max bound to the guess and keep calculating. Otherwise, we set the min bound to the guess and keep calculating. Either way, we continue to iterate through the loop. Now, we want to make a flow graph for this code. To do so, we'll look at three kinds of flow graph constructs. One for sequential code, one for conditional code, and one for iterative code. Each construct contains nodes and edges. In this construct for sequential code, we simply have two nodes and an edge going from one node to the next. Notice that we're not picky about the number of nodes we have here. In fact, sometimes sequential nodes are left out of the flow graph altogether because they don't contribute any information toward the cyclomatic complexity metric. Our next flow graph construct is for conditional code, or if statements. In this construct, we see two nodes, with two edges going between the nodes in the same direction. One edge represents the true branch of the condition, and one edge represents the false branch of the condition. There's no convention regarding which edge represents which branch, just as long as both branches are represented. Finally, we have the flow graph construct for iterative code. This has two nodes. One of the edges from the top node goes directly to the bottom node. This edge represents what happens when the while condition is false. You break out of the loop. The other edge circles back to the top node. This edge represents what happens when the while condition is true. The code continues to iterate. Note that other flow graph constructs exist, for switch statements, for example, but the three constructs we covered here are the most fundamental and should give you a good idea of how to construct a flow graph. Now let's construct a flow graph for the square root method. I highlighted the selection statements and the iteration statements as these are the statements that directly contribute to the flow graph. Essentially, any statement that includes a condition will contribute to the flow graph. Let's gray out all of this code so that we can better see which specific portions of the code are represented by what flow graph constructs. First, let's start with the sequential code before the if statement and after the while loop. Ignoring everything else for the time being, this gives us two nodes connected by a single edge. We'll look at how to calculate the cyclomatic complexity metric at the end of this exercise. But it's good to know that the cyclomatic complexity for sequential code is 1, because there's exactly one path through the code. Now let's look at adding that first if-else statement to the code. We do this by adding two nodes with two edges between them. One edge for true and one edge for false. If we stopped here and did not include the while loop in our code, the cyclomatic complexity of this code would be 2, because there are two distinct paths through the code now. one that chooses the true branch of the if statement and one that chooses the false branch. Now let's add the while loop to the flow, but without adding those internal selection statements. We add the while loop by adding two nodes and two edges. One edge goes to the next node, and the other edge circles back to the node it started from. Now let's add the outermost if statement from that loop. Since the if statement is inside the loop, it gets added to the looping edge, the one that circles back on itself. When we add the next if statement, we simply pick one of the edges of the if statement we just added to represent the else edge, and add the if statement to that. So that represents the inner if statement. And now we have a completed flow graph for the square root function. And now that also means we can calculate the cyclomatic complexity of the method. As it turns out, there are actually a few different ways you can calculate the cyclomatic complexity from just looking at the flow graph. First, you can simply count the number of predicate nodes and add 1. Predicate nodes correspond to conditions in the code. Predicate nodes are nodes that have two outgoing edges instead of just one. The nice thing about this way of calculating the cyclomatic complexity is that you can simply eyeball the code to get this number. Just count the number of conditions in your code and add 1 to it. For example, in this code, there are 3 conditions coming from if statements and 1 condition coming from the while loop. That makes 4 conditions, and each of those conditions, by the way, is represented with a predicate node in this graph. Add 1 to those 4 conditions, and you get a cyclomatic complexity of 5. Next, you can count the number of regions in your graph. Here there are 5 regions. One region is in the space created by that first if statement. The while loop contains 3 separate regions. And there's a region that surrounds the entire graph. So don't forget to count the surrounding region as a region. The final method is to count the number of edges, subtract the number of nodes, and add 2 to the result. I'll let you do this as an exercise, but you should come up with 5. By now, you should realize, based on our discussion of paths and path coverage in the previous video, that cyclomatic complexity does not correspond to the total number of paths in a program. In fact, it corresponds closely to branches and branch coverage in a program. What follows is a strategy for ensuring that you have covered all the statements and branches in your code. With modern tools like ECL-EMMA that tell you when you have not achieved 100% coverage, there's less need for this strategy, but it's instructive nonetheless. You start by calculating all the linearly independent paths through your code. You find a linearly independent path by choosing the shortest path through your flow graph that covers a new edge. For example, the first path chosen will pick either edge from the first if statement and will skip the loop. The second path will choose the other edge from that if statement, and it'll also skip the loop. The third path will choose either edge and will go through the loop in the shortest way possible. The shortest way through this loop is to skip the nested if statement. The fourth path will go through one edge of the nested if, and the fifth path will go through the other edge of the nested if. Together, these 5 paths denote linearly independent paths from the square root function. In white box testing, your goal should be to write enough test cases so that you cover all of the linearly independent paths. As mentioned, this is equivalent to achieving 100% statement and branch coverage from a tool like ECL-EMMA. Instead of trying to write test cases that achieve this from scratch, let's go back to the black box test plan we developed in the last video and see how many of these 5 linearly independent paths are covered by those 3 test cases. In the first black box test case, we're looking for the square root of 0. It turns out that this test case covers a relatively short path. The condition in the if statement before the loop is false. We go through the loop, and the condition of the first if statement inside the loop is also going to be false, which means we only go through one iteration of the loop. If you go back and look at the 5 linearly independent paths we came up with in the last slide, you'll see that this test case completely covers both paths 2 and 3. That means there are only 3 paths left to cover. The second test case also takes the false edge of the first if statement. On its first iteration through the loop, it takes the true edge of the outer if statement and the false edge of the inner if statements. Now, I didn't calculate beyond the first iteration of the loop, so it's possible that with subsequent iterations, it will also eventually cover the true edge of the inner if statement. However, even if we just stop at the first iteration, we see that it covers linearly independent paths 2 and 4. Since the first test case also covered path 2, we still need to cover paths 1 and 5. Fortunately, our last test case does this. Unlike the other test cases, it covers the true edge of the initial if statement, which means that path number 1 will be covered. Inside the loop, the first iteration takes the true edge of the outer if statement and the true edge of the inner if statement. And this takes care of path 5. Again, I've only calculated this for the first iteration. It's possible that with enough iterations, the test case will also cover paths 3 and 4. In fact, now that I think about it, every test case is going to cover path 3. Path 3 is the path through the loop in which the first if statement is false. If you go back and look at the code, this is actually the only way you can break out of the loop. So it actually turns out that our 3 black box test cases are sufficient to cover all 5 linearly independent paths. In fact, it looks like you would only need test cases 2 and 3 to cover all linearly independent paths, since all test cases must eventually traverse the false edge of that main if statement from the loop. And that leads to an interesting question. We started with 3 test cases that cover all linearly independent paths, and then we discover that we can cover all linearly independent paths with only 2 test cases. The question I'm thinking about is, do you think it's theoretically possible to cover all linearly independent paths with just a single test case? Please pause the video and try to answer this question. Ready? The answer is no. It is not possible to cover all linearly independent paths with just a single test case. And the reason has nothing to do with the loop. The reason is that there is no way to cover both the true edge and the false edge of that first if statement, that if statement outside the loop. That means we have to have at least 2 test cases to cover all linearly independent paths for this particular flow graph. And that's it for this module on software testing. This is Dr. K. I hope you learned something, and I'll see you in the next module.